Hi, today we are going to be talking about the gate-based quantum computing SDK from Automatski. So when you download the SDKs, there are two SDKs. You will get zip files like these. Initium is the quantum annealing SDK and Comenco is the gate-based quantum computing SDK from Automatski. If you go into this folder, you will find a lot of folders with programming language names, a contact us email address, a presentation, and some documents. So let us look at the presentation first. What is a quantum computer? A quantum computer is a computer based on physics that uses qubits to store variables and quantum properties like superposition, entanglement, quantum interference. And the operations in the computer are implemented using quantum gates, which are analogous to digital logic gates. This is what a quantum computer looks like from outside and from inside. This is the what is called a chandelier, and 90% of it, the golden color and the uh, circular plates that you see are basically the cooling apparatus and control wires. There is a small processor at the bottom tip of this chandelier, which is the actual quantum processor. Quantum computer runs circuits like these. These are quantum circuits. They have qubits on one side and they have gates, and then you measure them in the end and get the results. This is a 5 qubit circuit, and all these qubits start with a zero state by default. Zero state and the other state is basically one state, and you could have values in between also. But by default, all quantum circuits start with the zero state. This is a 2 qubit C naught gate, controlled NOT gate. This is a Y gate. H is a Hadamard gate. X is a NOT gate, and so on. This this dial kind of a thing is basically saying that you measure the qubit 0 and you retrieve the result classically. You measure the qubit 1 and retrieve the result classically, measure qubit 2, 3, 4, etc. Now, sorry, one thing about the measurements is that after you measure a quantum circuit, the qubits are going to be only in 0 or 1 state, and you will get combinations of such states as your answer. This is a 3 qubit circuit with the Hadamard gate acting on the first qubit and control NOT gates acting on the first and second qubit and first and third qubit. This is what the results look like. The results are a histogram. You can see that the quantum state 000 is mentioned here and 111 is mentioned here. This is the combination. And after measuring this circuit 1024 times, 517 times the system measured 000 and 507 times the system measured 111. This is the answer. So 1024 is the number of shots, and these are the counts. Usually at the end of every quantum circuit, you get a histogram of counts and states. Now let's try to build a quantum circuit in Python and execute it. We are going to build a GHZ state. GHZ state is basically a Greenberger-Horn-Zillinger state. It is a special type of state in which it has maximal entanglement, and the answer is only 000 or 111 with equal probabilities. So this is how you create a GHS state with 3 qubits, and this is the result that we are going to expect. So you import the Automatski library, start a quantum circuit with 3 qubits, apply Hadamard H gate on the 0 qubit, control NOT gate between the 0 and first 1 qubit, and control NOT gate between 0 and second qubit, and you measure everything. You measure all the qubits. This is the driver, and this is how you connect to backend system, which is basically Automatski's quantum simulators and quantum computers exposed on this IP address and port number 80. Then you run the circuit for 1,000 shots and retrieve the top 20 histogram results, or whatever, how many ever you want to retrieve. You get the measurements, you print the measurements, and then you sort the measurements and print a histogram chart on the screen. This is what it looks like. Uh, the GHz state is, all states are 000 and 111 with equal probabilities measured 1,000 times, so 500 times each. Now, there are hundreds of examples of quantum computer programming on the internet, courses on Udemy, Coursera, videos on YouTube to learn from. But you can get started with quantum computing and quantum AI examples in the Automatski's Comenco SDK. Programming quantum computers, especially gate-based quantum computers, requires mathematics, physics, chemistry, and programming skills. It requires training. It is not something that can be done casually. It requires a lot of practice. So the best way to get started is to download the Automatski Quantum Computing SDK and look at all the examples. And if you need production grade quantum computers, we have those too, but they cost millions of dollars. These are our offerings. Uh, these are quantum annealers from 5,000 to 1 million qubits, and these are gate-based quantum computers with 20 logical qubits through 1,000 logical qubits or more if you need. You can share these links with your friends and network. These are the links of the two SDKs from Automatski. And we offer a try, verify, buy for our production grade quantum systems. Let us know if you need to try out those systems if you're interested in buying them. Now back to the SDK. So you look at these folders, C sharp, Dart, etc. These are basically language bindings of our quantum gate-based quantum SDK in these programming languages. So you can use any of these programming languages to program a quantum Automatski's quantum computer. If you go into C sharp, you can see the program source code. If you go into Julia, you can see the Julia source code. So we are going to look at Python. Now, there is a benchmarking folder and there are a lot of benchmarks. If you know what that means and how to run them, you can look at that. Bracket, Circ, Classic, JAX Quantum, MyQLM, PyTorch Quantum, and Qiskit are basically frameworks for quantum programming. Native basically means that you can create a quantum program without using any of these frameworks, working directly with Automatski's quantum SDKs. This is a README file. If you open it, it will teach you how to create a Conda environment. Conda is a Python package manager, and these are the packages you need to install basically. And if you go into each of these packages folders like Qiskit, there is there might be another README file which tells you which other extra packages to install to run examples in this folder. If you go into Circ, there is a README file that says install Circ and PLY. Now let's go to native. There is a hello world example. Let us look at this example. Now we are going to create a GHz state with 7 qubits, or what, how many ever qubits you want. You start a quantum circuit with the given number of qubits and put the first qubit, put Hadamard on the first qubit, then on the rest of the qubits one by one. You put a control NOT gate and then you measure all. This is how you call the Automatski quantum systems on this IP address and port number. You run this quantum circuit with 1,000 shots and retrieve the top 20 histogram results. You print the measurements on the screen and then you plot a chart. So let's try doing this. This is the histogram and you can see uh, The two states are 000 and 111, all 7 bits, qubits, with equal probability, 500 counts of each. The total number of counts is 1000 shots. And this is the histogram printed on the measurements printed on the screen. State 111, 500 times. State 0000, it should be here, yeah, here, 500 times, and the rest of the states are 0. Now let's go into the Qiskit folder. We'll be running a Grover's example. So let's go into the Qiskit folder. This is the Grover's example. The number of qubits is 2, and the secret is, the Grover secret is 1, 1. So you start by putting all the qubits into a superposition by putting a Hadamard gate on them. Then CZ is the oracle that you implement across qubit 0 and 1. And then you implement the diffusion operator. You draw the circuit, show the circuit, and then you put measurements. And this is how you call the Automatski backend quantum systems. You run the Grover circuit with 1000 shots or 1000 repetitions and measure and retrieve the top 20 histogram results. You get the counts and you plot the counts in a chart. So and the chart should give you 1, 1 with the highest probability. So this is the Grover circuit. Hadamard gates on each of the qubit in the beginning, putting it into a superposition. This is the oracle, and this is the diffusion operator. And this is the histogram result. The secret was 1, 1, so 1, 1 got recovered with 1000 counts out of 1000 shots with 100% accuracy. So that's all we had for you today. If you look at these examples in the SDK, these have so many programming language bindings that you can create mobile apps, web apps. You can integrate Automatski's quantum systems into mathematical programming languages or Java, Ruby, Rust, or whatever that you desire. And this allows us to create native quantum AI HPC workflows. If you have any questions, please email us on info@automatski.com. Thank you very much.